All right, everybody at home, make sure this thing's working. Okay. All right, everybody at home, we're going to review LeChatlier's principle. If you're at home, you only really saw like a 20-minute ed puzzle, and you guys had that ed puzzle, people here, you had that ed puzzle assigned as well. Did you see my little note when I was talking about decay as a rate instead of an expression? I put a little note in there about the first 3 minutes in. I'll pretend you're all shaking your heads. I don't know why I said that, but that was stupid. So this is our second LeChatlier review, then we're going to be done with it. This may end up an ed puzzle. It may end up just being a lesson, but here we go. Okay. I'm trying to zoom in tight on the board here so these people at home can see it. All right. Now, we've got an expression. We're going to build a factory, and we're going to control this reaction, and we're going to produce dinitrogen trioxide and chlorine monofluoride gas. And we're going to do that by our reactant is going to be oxygen difluoride and nitrogen trichloride. So there we go. Now we're going to build a machine with here with some inputs. All right, here's the input. This input right here is going to let in some oxygen difluoride, and then this valve right here is going to let in some nitrogen trichloride. And then here is our machine. And then on top of the machine, we're going to have it hooked up to a compressor that can change the pressure. And then we're going to have two outlet valves over here on this one. Two outlet valves. Okay. The lighter gas we'll try to get out of the top into O3. No, that's backwards. The lighter gas we would try to get out of the top, okay? And that would be chlorine monofluoride. And we have a valve down here for the dinitrogen trioxide. And you can see this expression is extremely exothermic, so it gives off a lot of heat. Another way we can control this beside the pressure is we'll have a heater right here. And we can heat this thing up or cool it off, okay? So let's talk about this. For every expression, or for every equation you can write, you come up with a number called K. The K of equilibrium is called the equilibrium constant, okay? And what that is when this reaction is happening in this tube and it is at equilibrium, that means that the reaction is going both forward and backwards at the same rate. That's what equilibrium means. Equilibrium does not mean at all that there are equal amounts of these compared to these. Does that make sense? Equilibrium means what's happening in your container is steady. The forward and reverse reactions are occurring at the same rate. Now, when that happens, these products aren't necessarily in balance. As a matter of fact, the products and the reactants are, I can't imagine them ever being perfectly in balance, as in having the same amount of each. What is balanced is the forward and reverse rate of the reaction. At that point, you will have different numbers of these, and later in class we'll write an expression that will give you a number for the K, all right? So just know that the equilibrium constant is a number that is achieved when the forward and reverse reactions are happening at the same rate. If it is higher than 1, that means you have more products. If it is lower than 1, not negative, but lower than 1, that means you have more reactants being made. Does that make sense? Or you have more reactants in the container. All right, I'm going to open up a valve. Psh, I'm going to let in some oxygen difluoride. Open up this valve. Psh, I'm going to let in some nitrogen trichloride. So there'll be a bunch of these in there floating around. All right? And they're moving around. We know about kinetics. These things are moving around. They're banging into each other. And they're banging into each other, and they're going to be making some of these products here, right? Davis, you're missing literally everything I'm talking about. Come on, come on, come on. So these things are banging into each other. We're going to be making some N2O3, and we're going to be making some CLF from the collisions of these guys. Make sense? So we're going to have some products in here, and we're going to have some reactants in here. And this reaction is going forward. We're making some of these, and it's going backwards. Forward and backwards at the same rate when we're at equilibrium. Right? Now, LeChatlier's principle says that we can change what's happening in here by adding or removing some of these gases, or by changing the pressure, or by changing the temperature. Okay? Right. Here we go. I'm going to open up a valve. I'm going to let in some more OF2. Now, if I add a product, some more OF2, do you not agree that the likelihood for more collisions has gone up? Right? So if I open this valve, let in some OF2, this equation, to go back to being at equilibrium, will have to do what we call shift to the right. If you add some of this, it's going to shift to the right, and it's going to make more of these as a result. Right? And you understand why it would have to do that, because now there's more OF2s in there and a higher likelihood of collisions. Right? So adding a reactant causes a shift to the right. You make some more product, boop, 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 and then it goes right back to being at equilibrium again. So this shift is brief, okay? And then we go right back to having the forward and reactions equal again. But when you first put in some OF2, whoop, it shifts to the right. Then it bounces back out. Does that make sense? So this system has a response. That is LeChatlier's principle. Okay? Briefly, what if I added some more N2O3 in there? Guess what? Now there's more N2O3 in there, so you have more opportunities for this stuff to break down and go backwards. If you add some more product, then you get a brief shift to the left, right? Because now if you add some more of this, you have more opportunity for molecules in there to break down back into these guys, correct? So if you add a product, you have a shift to the left, and then it balances itself back out. And then the forward and reverse reactions are equal again. Everybody feeling that? Okay, I'm going quickly because we've already talked about this, even though it is a fairly difficult concept. All right, now, one thing I should have done already is balance this. And I have to balance it to answer the rest of the questions. Let's see here. I'm going to, got a 3 there, 3 there, 3 there, maybe 6. I hope I can pull this off. 3, 6. Oh, 2. Yes. All right. 3, 2, 1, 6. Everybody like that? Everybody in this present in the class, can you check on that for me? Okay, so this equation is balanced. I had to balance it to answer the next question. Notice all of these are gases, right? Right? Now we're going to talk about not adding more of each, but now we're going to use this compressor. And we're going to change the pressure in here. If we add pressure to a system, do we end up with more or less gas bubbles? Gabby, what do you think? Huh? Say the opposite of that. Gabby was absolutely right. No, all right, I'm just messing around with you. Okay, look, check this out, people at home. This is a soda that I've shaken up. Now, if I open it, that decreases the pressure. And what would you see? Would you see more or less gas bubbles? Right. So less pressure equals more bubbles. Everybody agree with that? Less pressure equals more bubbles. That's how gases work. So let's crank up this compressor and add a lot of pressure to this system. If we add pressure, we're going to shift more pressure. Means less gases. So, we look at our formula. We add pressure to the system. We are going to shift to the left. Why, you might add? The left has 1, 2, 3, 4, 5 gases. The right has 1, 2, 3, 4, 5, 6, 7 gases. Does that make sense? So adding pressure to this system will cause a shift to the left. Removing pressure will cause a shift to the right. Does that make sense? And then the system would adjust and go right back to its equilibrium number. So that's how pressure works. One last one. Ready? One last one. The last thing is different. The last piece of this puzzle, we're going to stop messing with the valves, okay? We're going to stop cranking up the compressor. The last thing we're going to do is mess with the heater. Okay. If I crank the heater up and make it hotter, something is going to happen. For this reaction to run in this direction, it needs to give off heat. It is very exothermic. It has a negative delta H of 300 kilojoules. Okay? I'm making these numbers up. For this thing to run this way, it needs to be able to give off heat. If you add heat to it, then you're going to mess that up. It's just like your car engine. If your car engine is running properly, it is very exothermic. And you constantly have to cool it off using the radiator and the fan. If you stop using the radiator and the fan, and you drain all the fluid out of your radiator, and you cut the fan off, then your car will get hotter and hotter, and then it will stop working. Exothermic reactions operate better in cooler conditions. So if you heat up this reaction, this one can't go this way as well. So that would cause a shift to the left. And the K would stay out of whack. Temperature is the only thing that will change the equilibrium expression for what's happening in here permanently. Temperature doesn't cause a temporary shift. Temperature causes these products to change what they're doing, and then it changes the whole equilibrium in here, changes everything, and it stays out of whack until you change the temperature again. Temperature is the only adjustment we can make that will actually change the K, okay? It's the only one. Now, if we added heat, this would shift to the left. What would happen if we cooled this off? What happened if we cooled this? Which way would it work better? It would work better to the right, because then it can give off its heat, right? It's producing dinitrogen trioxide, chlorine monofluoride, and heat. So if we cool it off, it can produce more heat, just like your car engine. And the K will stay out of whack. So that is the long and the short of LeChatlier's principle, except for one more thing. That was a review. Here's the one more thing you have to learn. You know what? Yeah, I'm going to do it. Ready? Here's the one more thing that you have to learn, people. We are going to actually learn to write the K for this expression. Okay? The K EQ is equal to the product, you're going to write this down, the product of the reactants no, excuse me, the products raised to the power of their molarity over the reactants, over the product of the reactants. By product, I mean the multiplied answer, raised to the molarity of theirs. So you may be wondering, what? And that will be that'd be a really good answer. Jot this down real quick and I'll show you. All right, ready? The products raised to the power of their molarity divided by the product of the reactants raised to the power of their molarity. What do you mean, Mr. Perkins, by the product of the reactants? I mean the multiplied answer, like product in math. Ready? Here it is. The equilibrium expression you would get from this, and it will be no more difficult than this for high school science, for this year anyway. NCl3 to the second, see how this is the molarity, times I should have put OF2 first, doesn't matter. OF2, let me put OF2 first. It just wasn't. Ready? OF2 to the third NCl3. No. The products go on top. Yeah, I did this yesterday too. I don't know why I'm writing this backwards. I did it yesterday. Lord, children, just forgive me. If I thought it was that bad, I would erase it from the video, but I'm not going to do that because I totally forgive myself for this mistake. Forgiveness is the first step. All right. There you go. The products over the reactants. That is the equilibrium expression. Okay? That is the equilibrium expression. It is usually a very large or a very small number. If this number comes out to be something that's very, very large, like 1.7 times 10 to the 20th, then this reaction would favor the products. If it turned out to be a very small number, like you'll see later, 1 times 10 to the negative 14th, something like that. See how this number is far below 1? This point 0.000000000000001, right? If it's a very small number, then it favors the reactants. Does that make sense? So this is decay. And we'll touch on it again at the end of class.